All right, welcome back. So today we are going to introduce the ratio test for series. And to introduce the ratio test for series, it is hard not to discuss geometric series because geometric series are really the inspiration for the ratio test. So when you look at geometric series, well, let's just remind ourselves, this is a geometric series. We've got a number plus a number times r plus a number times r squared. That number r is the common ratio. Well, when you have a geometric series and you take any term of the series and divide it by the previous term, you get r, right? Take ar cubed divided by ar squared. The a's cancel, most of the r's cancel, you get exactly one r left in the numerator. Do that with ar to the fifth divided by ar to the fourth, you'll get r again. And note that this ratio in absolute value was related to convergence, right? Because when the common ratio, this r, was less than 1 in absolute value, we had convergence with our geometric series. And in fact, when the absolute value of the common ratio, the absolute value of that ratio was greater than or equal to 1, we had divergence. And so it suggests that the ratio of subsequent terms is related to convergence of a series, well, in the case of geometric series. Well, what if we just had a generic series of a1 plus a2 plus a3 that's not necessarily geometric? Well, to draw a comparison to a geometric series, what we're going to do is not just look at a ratio of the terms, because in principle, it's unlikely that the ratio is constant here. If the ratio were constant, we'd have a geometric series, and we know how the series would converge anyways. So let's assume that an plus 1 over an is whatever it is, and instead of looking at that number, which would not be a number most likely, let's look at the limit as n goes to infinity. So what happens as we get late into the series? Because late into the series is going to determine whether or not the series converges or diverges. It's never the first 10 terms or the first 100 terms. It's always the last infinitely many terms. So what if, as we get close to infinity, the ratio of subsequent terms was equal to some number in the limiting case, or was approaching some number? Well, hey, then we are drawing a comparison to a geometric series. And depending upon what that number is, if that ratio of subsequent terms in absolute value has a limit that's less than 1, we are essentially drawing comparison to a geometric series with common ratio less than 1. And geometric series with common ratios less than 1 will converge. In fact, they converge absolutely. The absolute values are a piece of the puzzle here. I'm not going to go through the proof of this, but the fact that the absolute values are here is why we get absolute convergence. You can actually do a corresponding version of the ratio test without absolute values and not get absolute convergence, but we're not going to worry about that because it really doesn't help us out any. What if, on the other hand, the limit of this ratio, an plus 1 over an, the limit of subsequent terms, was approaching a number bigger than 1? Well then, hey, we're going to get divergence here. You can even think about that in terms of the test for divergence. If the ratio of subsequent terms is bigger than 1, the terms are getting bigger and bigger in absolute value. There's no way that those terms are going to converge because all convergent series have terms that tend to 0. And then, here is where the limit has its sort of quirkiness to it, right? Because a limit is an approximation, not an exact thing. The limit is about what things converge to, not what things actually are. And so, in fact, in the case where n plus 1 over an is equal to 1, the ratio test will be inconclusive. And I'll show reasons why that is the case. So let me scrub the slate clean, show some examples, and nail down some intuition related to the ratio test. All right, so let's nail down some intuition related to the ratio test. I've got two geometric series here. Hopefully these geometric series will work nicely with the ratio test because the ratio test was trying to draw a comparison to geometric series. I've got two non-geometric series here to emphasize how the limit associated with the ratio test is, sensitive in the sense that there is some inconclusivity which can occur when the limit associated with the ratio test evaluates to be 1. So to process this one here and to process any ratio test, what do? We consider a limit as n goes to infinity of an plus 1 over an, which in this case is a limit as n goes to infinity of what? Well, the an plus 1th term is 2/3 to the n plus 1. The anth term is just 2/3 to the n. And when we cancel here, all the 2/3 downstairs cancel, only 1 2/3 upstairs remains. And now we're just taking the limit of 2/3, which is 2/3. Hey, since 2/3 is less than 1 here, the ratio test says we would have convergence. So this would give us convergence by the ratio test because the limit associated with the ratio test turned out to be 2/3. So let me write this out here, scrubbing away the work that I just did. We'll say here, the limit associated with the ratio test was equal to 2/3, which is less than 1, which implies convergence by the ratio test. Okay, sweet. What about our next example? Well, similarly, if we're going to apply the ratio test here, we're going to take a limit as n goes to infinity of absolute an plus 1 over an, drawing a comparison to a common ratio here. What is the n plus 1th term? Well, hey, that's 5/4 to the n plus 1. What's the nth term? Well, hey, that's just a carbon copy of what's in our functional expression for our series terms. And whenever we cancel this out, n of the 5/4 downstairs cancel with n of the 5/4 upstairs, leaving us with exactly 5/4. And hey, 5/4, that's bigger than 1, so we would get divergence here via the ratio test. So scrubbing this away, the limit associated with the ratio test is giving us 5/4. And since the limit associated with the ratio test gave us 5/4, which is, whoops, greater than 1 in this case, we would have divergence by the ratio test. So we get a nice warm hug from the ratio test in that the expectation that we have based upon the nature of these two geometric series, common ratio less than 1, common ratio greater than or equal to 1, plays out how we would hope. Now, what about these two over here? Sum 1 over n, sum 1 over n squared. Well, let's apply a ratio test to them. You take a limit as n goes to infinity, as always, of an plus 1 over an. Well, in this case, looking at the 1 over n, what's the n plus 1th term? Well, that's just 1 over n plus 1. And, well, what's the nth term? That's just 1 over n. Well, we've got a double-decker fraction here, so we're going to have to keep change flip. So be it. You know, we're calculus students. We can handle this. We get n over n plus 1. And now we get an equal heavy rational expression, right? We have degree 1 upstairs, degree 1 downstairs. So what do? We take the ratio of the leading coefficients, which is 1 over 1, and this limit evaluates to be 1. Ooh, ratio test inconclusive in this case. So check it out. For sum 1 over n, we got the ratio test is blind to this series. The limit here came out to be 1. Ratio test inconclusive. Now we know that sum 1 over n is divergent. It's the harmonic series. We've seen that for a while. But the ratio test is not able to detect whether or not sum 1 over n is convergent or divergent. And check it out. Why L equals 1 is inconclusive, we'll be able to see from this last example. Let's look at sum 1 over n squared. If we want to apply a ratio test to it, we're going to, like we always do when we take the ratio test, is we're going to consider a limit as n goes to infinity of an plus 1 over an. But what is the n plus 1th term here? Well, that's 1 over n plus 1 quantity squared. And what's the nth term? Well, that's 1 over n squared. Yes, double-decker fraction, but so be it. We can handle this. Whenever we compute it out, we get n squared over n plus 1 squared. And here, if you FOIL this out, you'd have a degree 2 thing downstairs. You got a degree 2 thing upstairs. That's an equal heavy rational expression. And when it comes to equal heavy rational expressions, the limit as n goes to infinity is just the ratio of the leading coefficients, which this comes out to be 1 as well. But wait a second, that means the ratio test is inconclusive for this series too. And check it out, this shows a nice fact about the ratio test. Here we get L equals 1, ratio test inconclusive. Now why is the ratio test inconclusive when the limit associated with the ratio test comes out to be 1? Well, because sometimes when the limit is 1 associated with the ratio test, you end up getting that for a divergent series, and sometimes, like 1 over n squared, this is a p series that converges. Well, sometimes the L equals 1 occurs on a convergent series. So the L equals 1 occurred here on a convergent series, the L equals 1 occurred here on a divergent series, so the ratio test can't tell you what's happening when L is 1. But when L is less than 1, you get not only convergence, actually, my goodness, I should put absolute convergence on this, because that is, in fact, true. And in the case where the limit associated with the ratio test is greater than 1, you get divergence. So, well, hey, all these examples, we kind of already knew how these ones were going to play out. What about examples where the ratio test gives us something new and something different? So let me pause here. We'll come back and hit some new examples so that we can really see the ratio test shine in new territory. All right, before we jump into our novel territory with the ratio test, I just want to make a note so that we don't get sort of ahead of ourselves here. And check out what happens when you have a factorial inside your summation. I claim that factorials are ratio test friendly. Check it out. if we look at a ratio of the n plus 1th term divided by the nth term, who knows what else is in the sum? But let's just assume we've got an n factorial in there. Well, upstairs we have n plus 1 factorial. Downstairs we've got n factorial. So this would be like n plus 1 times n times every number less, right? N plus 1 times every number less than n plus 1, which, well, would include the number n if you think about it, right? This would be like 5 factorial over 4 factorial. And in the expansion of 5 factorial is a 4 factorial and just one extra term, namely the 5. So whenever you take the expression of n plus 1 factorial and divide it by n factorial, it might be easiest to take that extra factor of n plus 1 and factor it away from the rest of the factors of n factorial. In which case, the n factorials upstairs and downstairs would cancel, and you'd be left with just n plus 1 upstairs. Hey, factorials work nicely with the ratio test because when you take n plus 1 factorial divided by n factorial, you just get n plus 1. That suggests that when you have a factorial, maybe the ratio test is going to come into play. Another term that works nicely with the ratio test is whenever you have terms that involve k to the n here. K is some constants. Maybe it's 2 to the n or 5 to the n or a half to the n. Who knows? Who cares? Whatever the constant is. If you've got the n in an exponent, check it out. When you take the n plus 1 term over the n term, who cares what else is in the sum? But if you've got a k to the n in there, upstairs you'd have k to the n plus 1. Downstairs you'd have k to the n. And all that other stuff will do what it does, but check out how the k to the n's cancel. Well, hey, the n factors of k downstairs will cancel with n of the factors upstairs, leaving just one k upstairs. So k to the n's work really nicely with the ratio test. And when I scrub the slate clean and show us a few examples, you'll see all the examples I'll show will involve factorials and exponentials because those are expressions that work really nicely with the ratio test. All right, so let's hammer out two examples. One of them is n squared over 2 to the n. The other is 4 to the n over n squared. Let's just remind ourselves, we said earlier when we had factorials or when we had constants to the nth power, those exponentials, those worked well with the ratio test. Note we've got a 2 to the n here, that's an exponential. That feels like it might work well with the ratio test. Here, gosh, we've got both of them going on. We've got exponential and factorial. That feels like a ratio test might be coming into play. So let's check this one out. We're going to apply the ratio test to this. And when you apply the ratio test, what do you consider? You always consider a limit as n goes to infinity of an plus 1 over an. And in this case, and in most cases, in fact, you'll end up with a double-decker fraction. The numerator here is going to be what? N plus 1 squared over 2 to the n plus 1. And the denominator is going to be just n squared over 2 to the n. This is in absolute values, but so be it. We can handle it. Whenever you keep change flip to multiply this out, what I like to do is almost imagine here the flipping, and then maybe I'll write the 2's over one another because those are going to cancel nicely. And then maybe I'll write my n plus 1 squared over n squared because those are going to cancel nicely. Now, what about the 2's here? The n factors of 2 upstairs are going to cancel out completely, and downstairs, all but one of the factors of 2 will get canceled away. What about the n plus 1 squared over n squared? Well, hey, that's like a n squared polynomial over an n squared polynomial. That's an equal heavy rational expression. Just to be precise here, I'll use the limit laws to write this out. We'll have the limit of 1 over 2, we've simplified that one already, times the limit as n goes to infinity of, this is going to be, I'll write it as n squared over n squared. Well, n squared plus other things. If you FOIL this out, you'd get something in terms of n squared. But the key is that you've got an equal heavy rational expression, and an equal heavy rational expression polynomial on top and bottom limits as n goes to infinity to the ratio of the dominant coefficients. And so put this all together, what do we get? We get 1/2 times 1, which is 1/2. What does that 1/2 mean? The 1/2 that pops out of the ratio test means that our series here is more or less, as n goes to infinity, similar to a geometric series with common ratio 1/2. Well, common ratio 1/2 means we're going to have convergence here by the ratio test. And in fact, not just convergence, we'll have absolute convergence. And the reason here was because the limit associated with the ratio test came out to be 1/2. Incidentally, this relates to the fact that we had that factor of 2 to the n downstairs, and that factor of 2 to the n sort of dominated the polynomial of n squared and led to that 2 that resulted in the denominator. So as n gets large, that 2 to the n dominates the expression, and we ended up getting the limit to a half. But it really takes showing all of the details to see why that's the case, because that's not necessarily intuitively clear just from the get-go. All right, what about this 4 to the n over n factorial? We're going to apply a ratio test to it as well. So like all ratio tests, what do? You consider a limit as n goes to the infinity of an plus 1 over an, which in most cases comes out to be a double-decker fraction, just like here. So the an plus 1 term is going to be 4 to the n plus 1 n plus 1 factorial. And then the an term is going to be 4 to the n over n factorial. The an term is really just a carbon copy of the explicit expression that's inside your sigma notation to begin with. Now, we've got a double-decker fraction, so be it. We've got to keep, change, flip. We multiply by n factorial over 4 to the n. And what I like to do is sort of like arrange my terms of like kind with one another. So if I put that 4 to the n plus 1 and the 4 to the n with one another, and then the n factorial over n plus 1 factorial, that will make it easier to see what happens. In fact, hey, these cancel about as well as they possibly can. The n factors of 4 downstairs will cancel with all but one factor of 4 upstairs. And remember how the factorials canceled? When you think of like 4 factorial over 5 factorial, the 5 factorial is just 5 times 4 factorial. Well, that means that the n factorials will cancel, and you'll be left with just n plus 1 downstairs. Well, hey, that all canceled away very nicely. When you look at this now after the cancellation, what do we get? Over here, we just had a 4, and then we have 1 over n plus 1. But now check that out. What happens here? We're letting n go to infinity, and we have 4 times something. That something is going to 0, and 4 times 0 is 0. And so, hey, the ratio test gave us a limit here of 0. Which means, as weird as this sounds, this series, as n gets big, is like a geometric series with common ratio 0. My goodness, the terms of this series must get really small as n gets big, because common ratio of 0 would basically zero out the terms. And so here, because we got a limit of 0, we get absolute convergence by the ratio test. I don't want you to think that just because these two examples converged via the ratio test, that we always get convergence via the ratio test. That is certainly not the case. In fact, if we took the two summations that we were looking at in these two examples, and we just switched the numerators and denominators, we would get a limit of 2 in the first case, a limit of infinity in the second case, and that would give us divergence in both cases. So let me write that down just so that we have this. I won't go through the details on the computation because it's analogous, but if we had 2 to the n over n squared and we applied the ratio test, the limit associated with the ratio test would be 2 here, which would imply divergence by the ratio test, because when the limit associated with the ratio test is 2, we're essentially drawing comparison to a geometric series with common ratio 2, which diverges, because in geometric series, when you have common ratios, anything 1 or bigger, you get divergence. What about over here, if we instead looked at the example sum of n factorial over 4 to the n, and here we would apply our limit, we would get 1 over 0, which would be infinity. And so here we would get something that would be sort of just unbelievably divergent, right? Because the terms here would be getting so gigantic so quickly. Anytime the limit associated with the ratio test is bigger than 1, here we're saying we're essentially analogous to a geometric series with common ratio infinity. Holy moly, those terms get big. This would give us divergence by the ratio test. So right, the ratio test doesn't give you convergence all the time. It's really sensitive to sort of what's upstairs and what's downstairs whenever you're looking at this ratio. But at least through the examples that we've seen, you can see sort of why the ratio test needs this inconclusivity in the L equals 1 case, and then how the ratio test sort of manifests, and almost what to look for in terms of when to apply the ratio test strategically when you've got those exponential terms, and whenever you've got those factorial forms, the ratio test works great. So this should get you off the ground with the ratio tests, and hopefully this helps you in your progress of study.